Good morning. Today my topic is no load test and block rotor test of three-phase induction motor. No load and block rotor test of three-phase induction motor. First, we will see the no load test. Okay, this is the diagram of no load test. There are three-phase supply we are giving to the stator of the induction motor. Okay, and there are three ammeters we are connecting it to measure the line current of three-phase line, and there will be two wattmeters to measure the power. Okay, one wattmeter to measure the power for W1, another wattmeter will be W number 2. Okay, W2, and there is one voltmeter to measure the output current across the two phases. Okay, so this diagram will be in a laboratory. We are using this experimental setup. Okay, this is the load, this is a breakdown load. Okay, this is the load. Okay, this load only we are placing it. Okay, the load, because this is breakdown, here belt arrangement will be there. Okay, and here if you release a load, okay, so the machine will be starts running smoothly. Okay, during this time the slip is n equal to ns, n equal to ns. So there are three parameters we are measuring. One, v naught. Okay, this is v naught. Here only we are measuring the v naught. Okay, and here this is I naught. I naught you can measure it for any phases. Okay, any phases, whether it will be R, Y or B. Okay, R, this one is R, Y and B, and W1, W2 for 2 wattmeters we are measuring it. Okay, in this test the motor is made to run without any load. Okay, you need not to apply any load, so therefore the speed of the motor is very close to the synchronous speed. In no load, the speed of the motor, that is nr equal to ns. So the rated voltage is applied to the stator. The input line current means I naught, and the total input power W1 and W2 is measured. The two wattmeters are used to measure this total input power. As the motor is on no load, the power factor is very low, which is less than 0.5. Okay, that is the power factor cos phi is less than 0.5. So if it is measured less than 0.5, now there are two wattmeters are there. In that one wattmeter will read negative value. It is necessary to reverse the current coil or pressure coil connections, the such a wattmeter to get a positive reading. This reading must be taken negative for the further calculations. The total output power, input power W0, which is equal to W1, because there are total two input powers we are measuring. One is W1, another one is W2. So therefore W0 equal to W1 plus W2. Okay. Where W0 is the power input in watts, V0 is the applied voltage per phase, I0 is the applied current per phase. Therefore the calculation is W0 equal to root 3 into V0 I0 cos phi naught. Therefore cos phi naught is equal to W0 by root 3 into V0 I0 cos phi naught. This is the formula for power factor, no load power factor. Okay, where V0 and I0 are line values. This is the equivalent circuit of no load test. The voltage and I0 is flowing. This there are two resistors, the reactance value, because this is one coil. Okay, this is a coil. So in this coil there will be a resistance and the reactance will be there. Okay, this R0, the current flowing in the resistance is active component current IW. The current flowing in the reactance term is the magnetizing component current. So active component we can measure IC or IW, and magnetizing component will be I mu or IM. Okay, I mu or IM. The parameters are IW, which is the formula is I naught equal to cos phi naught, and I mu equal to I naught into sin phi naught. Okay, only the IW will be applicable for cos, I naught, the sine term is applicable for mu. And the resistance, as per Ohm's law we know V equal to I into R. Therefore, R equal to V by I. And reactance also X naught equal to V naught by Im. Okay, these are the formulas will be available for no load test. So in no load test, what are the parameters we are measuring it? One is V naught we are calculating, another one is I naught, another one is W1 and W2. Okay, these are the four parameters we are measuring in no load test. The second one, and here in no load test, okay, while performing the no load test of induction motor in the laboratory, there are that is a changes in the speed, okay, power factor, stator current, rotor current due to fluctuation. When there is a changes in fluctuation in the applied voltage, the reading noted from the test will be more accurate. Hence it is also increases the accuracy of the calculation. While performing the no load test, the speed of the induction motor obviously remains constant during the test because the machine is running a normal speed. There is no variation. Okay, so when the machine speed will be vary if the heavy load on the motor, if you apply heavy load, if it changes the load, then the speed will be changes. Therefore here the applied voltage remains constant, so the speed of the motor will remain unchanged. When there is increase in applied voltage, the stator current, that is to supply a magnetizing component, that is Im, Im is supply, will also be increases. Okay, if Im increases, therefore the power factor will be decreases. The torque of an induction motor is proportional to flux, that is T is proportional to flux into Ia. Okay, phi into Ia. Okay, if torque is provided rotor current and flux generated on the by the stator winding, thus the flux will be depends upon the applied voltage. Okay, applied voltage, because we know phi flux is proportional to V. Okay, flux is proportional to applied voltage. When the applied voltage is kept minimum, okay, if you applied voltage is kept minimum, therefore the torque generated will remain constant, but the rotor current will go on increasing it. Okay, this is the no load test of induction motor. The second test which we are performing here, it is a block rotor test. The block rotor test is other name called it as locked rotor test. Okay, locked rotor test, the same arrangement we are using it, applied voltage and two wattmeters we are applying. Block rotor means what we are applying the full load, we are applying the full load, we are blocking it. Therefore the rotor not running. In this test, the shaft or motor is locked so that it cannot move and the rotor winding is short circuited. In the slip ring motor, the rotor winding, once the rotor winding is short circuited through slip rings, in case of cage motors, screw cage motors, the rotor bars are permanently short circuited. Okay. In slip ring motor, what happened? The rotor winding is short circuited through slip rings, but here in the screw cage, rotor bars are short circuited. So in block rotor test, the shaft of the motor is locked. Okay, the shaft of the motor is locked when you are giving the supply. Okay, so there are four parameters which we are applying here, which we are measuring it. The first parameter is VSC. VSC is the short circuit reduced voltage. ISC is the short circuit current, and WSC will be the short circuit input power. Okay, the formula WSC is equal to root 3 VSC ISC cos phi SC. Therefore, the block rotor power factor cos phi SC is equal to WSC by ISC. Okay, this gives the short circuit current. And in block rotor test, we are measuring the copper loss also. Copper loss, okay, no load copper loss. WSC losses is equal to 3 ISC square into R1E. Okay, R1E is the resistance. Okay, block rotor resistance. WSC by 3 ISC square. WSC is equal to 3 ISC square. And the reactance term also we can measure. Okay, reactance impedance term we can measure. Impedance Z1E equal to VSC by ISC. Okay, impedance. And the reactance term X1E equal to square root of Z1E square minus R1E square. Okay, so during this test, the stator carries the rated current, hence the stator copper loss is also dominant. Similarly, the rotor also carries a short circuit current to produce a dominant rotor copper loss. As the rotor voltage is reduced, the iron loss is proportional to the voltage. It's negligibly small. The motor is at standstill, hence mechanical loss, that is a frictional and windage losses is absent. Okay, is absent. Therefore, we can measure the short circuit current. ISM is equal to line voltage VL by VSC into ISC, and power WSM is equal to ISM by ISC whole square into WSC. Okay, these are the formula. Okay, where ISC is the short circuit current at reduced voltage, ISN is the short circuit current at normal voltage, WS is the short circuit current, short circuit input power at normal voltage. Okay, at normal input voltage. So in this method, the block rotor test is performed under normal operating conditions. When the rotor current and the frequency are on same conditions, generally the slip of the motor varies between 2 to 4%. Okay, it's 2 to 4%. Hence, the resulting rotor frequency in the range 1 to 2 Hz for the stator frequency of 50 Hz. This test should be performed at the reduced frequency. In order to obtain an accurate result, the block rotor test is performed at a frequency 25% or less than rated frequency. Rated frequency means you can perform less than 50 Hz. Here in this method, the leakage reactance at the rated frequency are obtained by considering that reactance is proportional to the frequency. However, for the motor less than 20 kilowatt rating, the effect of the frequency are negligible and block rotor test can be performed directly at the rated frequency. Thank you.